Okay, so now we're going to hear from Yvonne on neutrino lifetime constraints from precision cosmology.
Well, okay. So thanks for allowing me to speak here. And so I'm going to tell you about how to constrain the neutrino lifetime from precision cosmology. And what I'm about to tell you is based on a couple of papers that we wrote back in 2021 and 2022, actually 2020 actually. Okay. So everyone knows that there's a cosmic neutrino background, which was basically this thing that was produced 1 second after the Big Bang. And so we're left with this, these low energy neutrinos that are permeating all space. Now, well, essentially what's happening is that, you have at temperatures about 1 MeV, you have these neutrinos that are scattering off electrons, positrons, and they're in thermal equilibrium. And as the universe expands and cools, then eventually expansion will dilute the plasma and reduce the interaction rate of these neutrinos scattering off electrons and positrons. And from that point onwards, the neutrinos will free stream to infinity, which become the cosmic neutrino background that we can try to infer from cosmological observations. Now, so these days, there are several key predictions of the CNUB that you've heard in various forms in this meeting. So you can talk about, what is the energy density contained in this neutrino background at early times, which gives rise to this prediction of N effective is 3.0440, whatever, blah, blah, blah. You can have, that's from standard model physics. We also have the possibility that these neutrinos can form a subdominant dark matter component, where the omega nu, the reduced energy density in this neutrino would be between 0.1% to 5%. Okay, and of course, measuring this contribution is essentially tied to neutrino mass balance from cosmology. Now, yet another thing that you probably hear not so much about is that of testing the free streaming property of these neutrinos. In other words, another thing these neutrinos are not meant to interact with anything or with itself. The only kind of interaction it has is gravity. Okay, so this is also something that you can try to see if it's true or not in cosmological data. Okay, and the way to do it is, as usual, you look at these three pillars of cosmological observations, and particularly for the test of free streaming, what you want to be looking at is the imprint of free streaming on the CMB anisotropies. Okay, so that's what I'm going to be talking about, how we test relativistic neutrino free streaming. Now, as I mentioned earlier, once the neutrinos are decoupled from the plasma, they free stream to infinity. And that sounds like a maximally boring thing. They're just dying, right? But actually, it's not. It's because when we're thinking about neutrinos free streaming in the cosmological context, what they're doing really is that they're free streaming in an inhomogeneous background. And that has interesting consequences for these neutrinos. Okay, so imagine here that you have a series of potential wells which are representing the perturbations in the background. Okay, so you have a peak, a trough, a peak, a trough, a peak, and a trough. What's going to happen is that, and then you put a drop of neutrino fluid, which is dispersive. Okay, so think about, first of all, those neutrinos that are moving in the horizontal direction. They're either moving along a peak, or they're moving along a trough, or moving along something that is essentially flat. Okay, but for these neutrinos, they are just free streaming as if they are in a flat space or in a homogeneous isotropic space. On the other hand, if you think about those neutrinos that are either moving up or moving down, they are the ones that see the sinusoidal variation in the density. Okay, so what's going to happen with the neutrinos that are moving in either up or down direction is that as soon as they start to move, they're going to get dragged into the potential well. And that would make them pick up some kinetic energy and therefore increase the momentum. Okay, these are relativistic particles, by the way. So what it means is that if you have relativistic neutrinos free streaming in an inhomogeneous background, you're going to induce what is called shear stress. Or, in other words, momentum anisotropy. Okay, same thing. Okay, so that's the standard case. That's what happens in standard cosmology for standard neutrinos. On the other hand, think about a case where you may have some kind of self-interaction between the neutrinos with itself, let's say. Then what might happen is that you could have two neutrinos that are coming head-on. They meet each other, they scatter. And what scattering does is that it allows any momentum that is originally in this horizontal direction to be transferred to a different direction. Yeah, it can be totally transferred to a direction that is perpendicular to the initial directions of the two scattering neutrinos. And if this kind of process is happening fast enough, and you have very efficient momentum transfer from one direction to the next, then you can wipe out the anisotropy. And that's basically how we test for free streaming. We want to see if there is any neutrino shear stress. Okay. Now, why is neutrino shear stress testable? And that is because they actually leave an imprint on the metric perturbations at CMB formation times. Okay, so here is the line element written here in the conformal Newtonian gauge for those of you who do these cosmological perturbations. And essentially, it's just like the Freeman, Robertson, Walker metric, except that now you have these perturbations, which are essentially like gravitational potentials, if you like. Now, some of these have really interpretations of a Newtonian potential, but they are allowed to be different. These are two independent variables. And in fact, if you take the difference between phi and psi, okay, phi and psi, this difference is proportional to the shear stress. Okay, so in standard lambda CDM, the shear stress around CMB times is mainly coming from the free streaming of standard model neutrinos, yeah, ultra relativistic free streaming neutrinos, and a little bit from the photons after they decouple. Okay, so what it means is that if I am to remove the neutrino anisotropic stress from the universe, I'm going to end up changing phi and psi, and that's going to end up changing. And this is something that the CMB would know about, because when the CMB temperature fluctuations evolve, they will respond to any change that might be there in phi and psi, or the difference between the two variables. Okay, and that is the reason why it is that we can actually look for signatures of the neutrino shear stress, or the lack thereof, in the CMB anisotropies, in the TT power spectrum in particular. Now, this is not a new thing. It's been known for a long time. It was pointed out already back in 2005. This is Steen Hannestad's paper. What he did was to compute here in a solid line what you would expect for the CMB TT power spectrum if you have just standard neutrinos free streaming. So there's shear stress there. And then what he did was to remove by hand in his code the shear stress due to neutrinos. And what he found here is that the power would go up. Okay, this is one paper. There was actually another paper that came out at around the same time by Alessandro Melchiori and Roberto Ciotta. They modeled the things a little bit differently, but it's the same idea. They were also testing for anisotropic stress or lack thereof. And again, they saw that if you remove the shear stress in the neutrinos, you have an enhancement in the peaks here at multiples larger than about 200 or so. It's quite hard to mimic this effect by any other kind of physics, except maybe you can play around with the primordial fluctuation amplitude or the spectral tilt a little bit just to kind of cancel out this effect. But there's only so much you can play, so much, of this sort of game you can play. And apparently, even back in 2005, with only WMAP first year data, it was possible to exclude these no neutrino shear stress models at better than 2 sigma. That was 2005. Okay, this is like 15 years later. The game has evolved a little bit, and actually a more modern way of doing this sort of analysis is to split up the discussion about relativistic free streaming constraints or neutrino self-interaction into two kinds of limiting behaviors. So what people talk about these days is whether, for example, whether your new interaction could delay the decoupling of the neutrinos from the plasma. So essentially, you have your neutrinos interacting, and you have no shear stress when you enter into the CMB epoch, and then you ask the question about how late the CMB epoch can tolerate having no neutrino shear stress. Okay, so that's a decoupling scenario, and this can be realized if you have something that's like a 2-to-2 scattering contact interaction, so something mediated by a massive mediator. Okay. There's also the recoupling scenario, and the situation here is a bit more complicated, but I have a little schematic to illustrate what's happening. So this is temperature, and that's basically all the rates. And this is the weak interaction rate that drops down with temperature. That's the Hubble rate, the red line that drops down with temperature, and that's the standard weak decoupling. But if you have some kind of self-interaction mediated by a massless mediator, then you could also have an interaction, new interaction, that's the blue line that kicks in here, and then it crosses the red line at this point. So that signifies recoupling of the neutrinos. Okay, so this can be, as said, realized by 2-to-2 scattering mediated by a light scalar, light mediator, not necessarily a scalar, but it's also realized in the case of relativistic 1-to-2 decay. So I don't know what is 2-to-1 decay, 1-to-2 decay, and its inverse process. Okay, so in this particular scenario, what you're looking at is free streaming neutrinos entering into the CMB epoch, and then they recouple. Okay, and then you want to ask the question of how early in the CMB epoch can the neutrinos begin to lose anisotropic stress? Okay. So slightly different, but same idea. It's still shear stress that you're looking for. Okay, and that's what I'm going to be talking about mainly because it concerns decay. Okay, recoupling from relativistic invisible neutrino decay. So by invisible neutrino decay here, I'm actually talking about the same thing as the previous talk, it's non-radiative. We call it invisible in cosmology because we don't see the neutrinos. And so it's invisible for cosmologists. And I, of course, that for the neutrino community, it's neutrinos are visible. But anyway, it's the same thing. Now, so if you ask, do you have such a process happening in the standard model? And the answer is that, yeah, you can actually make it work. You can have a 1-to-3 decay. Problem is that this kind of process is highly suppressed. You get mass to the power 6, according to this paper. So if we only have sub-electron volt neutrino masses, then the corresponding neutrino lifetime would be like 10 orders of magnitude longer than the lifetime of the universe. So this scenario is actually not terribly interesting for us. So when we talk about invisible decay, most of the time we are really looking at something that's kind of more beyond the standard model. So a process such as this. So you have some heavier neutrino, heavier, not heavy, heavier. There's still some electron volt in mass. It decays into something that's lighter. It could be, an active neutrino or sterile, but it doesn't really matter. Okay, call it active for now. Plus some kind of boson. And in here, in this particular analysis, we have considered the boson to be massless. Okay. You do that obviously because you have more freedom in choosing the coupling string. Okay, and as it turns out, this kind of model can also be motivated somehow by having some kind of connection to the neutrino mass generation mechanism or dark matter. But okay, that's not my department. Someone else can would know better than I do. Now, so the question is, if I have a decay process such as this one over here, and I can calculate its decay rate, then, well, if I want to use relativistic free streaming requirements from the CMB to constrain this decay process, what are the key thing that I need to know is the rate at which neutrino shear stress is lost due to this decay process. In other words, what I need to find out is what is called the isotropization timescale. That's the key. I need to know that before I can map the CMB observations to the fundamental parameters of my model. Now, to calculate this thing, let me just tell you very briefly how we track neutrino perturbations, okay? And the way we do it is to adopt this relativistic Boltzmann equation written in this covariant form. And so that's the Liouville operator and this bunch of stuff here. The Christoffel symbols encode the gravitational effects. Okay? The conventional way of computing perturbations is to split my phase space density here into 2 parts. I have a homogeneous and isotropic part, plus this capital F here are the spatial perturbations. Okay. Now, for CMB studies, you can linearize the system because the perturbations are small. So we linearize this. The equations, the Boltzmann equation, and any gravity-related Einstein equation, for example. We go to Fourier space, and we decompose this F here into a Legendre series, which are in the direction of the wave vector of the perturbation to the momentum of the neutrinos. Now, once you've done that, and you integrate in momentum, that's a nice thing that you see immediately, and that is the monopole of this decomposition would correspond to perturbations in the depth of the neutrinos and the pressure. The dipole here would correspond to velocity perturbations. Okay, they don't matter for us. What matters are the higher multiples. Okay, so multiples larger than 2. Once you go to L of 2, 3, 4, 5, 6, whatever, these are the anisotropies. This is the shear stress, okay, in the neutrino fluid. Okay, so that's what we do in the standard case. If you download class or CAM, that's what's done in that black box. Now, what I want to do is to fold the decay process into this description. And the way I would do it is to, well, very simply, an integral. Okay, it's just exactly like how you track dark matter. You just add a collision integral to the right-hand side of the Boltzmann equation. So I can do that, and then I can just apply exactly the same recipe. Okay, you know, split, linearize, decompose. Now, what makes it kind of horrible is the form of the collision integral. It looks something like this. Okay, so you have your decay matrix element that you can put in here, and a whole lot of phase space integral that you need to do. You can do it. You know, just follow the recipe as outlined before. And if you once you expand out to L equals 2 moment, then the damping rate would correspond to the damping rate of the quadrupole would be the rate that would be the isotropization rate for our problem. Clearly, this is very tedious. It's like, you know, pages and pages and pages of calculations. But I want to stress that this is really the way to go, okay? Otherwise, you can get things very wrong, okay? Nonetheless, despite the ugliness of these calculations, sometimes the isotropization rates can be understood in very simple terms, okay? So let me show you how. So as a warm-up exercise, this is the isotropization from just a simple self-interaction. So here, I'm looking at a 2-to-2 scattering event. Okay, so I have one neutrino coming here, another coming here, they scatter, they go off. Okay, that's depicted by this picture over here. Now, if you look at the scattering of the two red neutrinos that are coming in, then the probability that the final state neutrinos, the green lines, to be emitted at any angle between 0 and pi is practically equal everywhere. Okay, so what this means is that if I have two beams of neutrinos and they go head on, they only need to scatter once before the momentum can be transferred into all angles. Okay, from 0 to 2 pi. Okay, so in this case, the isotropization rate is actually extremely simple. It's just 1 divided by the scattering rate. Sorry, the isotropization time scale is 1 divided by the scattering rate. Okay, this is an extremely simple example. Okay, that was easy. Now, let's try relativistic 1-to-2 decay, which is the process we want to describe. How long does it take for this process and its inverse process to wipe out momentum anisotropies? And let me give you a hint. It's not the lifetime of the heavier neutrino. And the reason it is not the lifetime of the heavier neutrino is as follows. Now, remember that I've been saying relativistic at every point, right? So this decaying neutrino is a relativistic particle. So it decays in flight. And when something decays in flight, the decay products are beamed. Okay, so that means that this phi particle, which we assume to be massless, when it flies out, the angle it makes with the original flight path of the heavier neutrino is essentially the inverse Lorentz factor. Okay? This is like second-year classical mechanics and relativity. I remember teaching that, so you should know this. Now, you can also ask what's the emission angle for the lighter neutrino. Well, as it turns out, if it's massless, then it will be exactly the same as theta phi. But if it's massive, you have a further suppression of this emission angle. Okay, so these angles are tiny if your decay neutrino is very fast. And similarly, if you look at what happens in the inverse decay process, the phi particle and the lighter neutrino have to have exactly the right kind of momentum, and they have to meet at exactly the right angle before they can combine to form a heavier neutrino. So what this means altogether is that if you want to use decay and inverse decay to bring a neutrino ensemble from this state of anisotropy to a completely isotropic system, it's going to take a very long time because it's just so inefficient at transferring momentum. Okay, so question is how long? Well, there were actually two works back in 2004 and 2005 that considered this problem to some extent. I mean, exactly the same problem. How long does it take for relativistic 1-to-2 decay and its inverse process to isotropize a neutrino ensemble. Well, neither work actually calculated the rate. They kind of guessed it. I mean, they didn't really guess it. They had an argument. But the time scale they used looks something like this. So this is the rest frame lifetime of the decaying particle. This is a Lorentz factor of that particle that's decaying. And there is a suppression factor here that goes like the inverse of the two angles. They actually just consider two masters daughters. So these two thetas were the same in these two works. And their argument is as follows. So just to simplify the discussion, let's forget about the fact that I have two different particles in the final state. Let's just assume that your decaying particle is decaying into two X particles, okay, just for simplicity. Okay, and we're just going to track one of these X's. And this X particle is emitted at an angle theta, which for simplicity, I'm just going to treat as a geometric average of the two emission angles. Okay, so this is what's happening. I have this particle that's coming in, the new H particle, and it decays. Now, when it decays into two X particles, I'm only going to track one of them, right? Then there's two possible mission directions, at least in my simplified description. I'm going to discretize this, okay? So it can either go this way, up, or you can go down at an angle theta. So up, angle theta, or down at an angle theta, okay? So it flies off, and then an inverse decay happen when this blue line here recombines with an X particle coming from the background. Now, it could recombine from one X particle coming from here, in which case the final heavier neutrino would be emitted in this direction, or this X here can recombine with this line here from the background, in which case the emitted new H would fly in this direction. Okay. Now, again, you know, if you have an isotropic background, then the probability of the new H taking this path or taking that path would be equal. Okay, so what it means is that if you look at the probability of the steps that will be taken by where the new H would end up after one decay and inverse decay process, you basically have this distribution. Okay, you could be spread out somewhere over 2 theta in angular directions. Okay. So if you keep repeating this many times, in particular, if you repeat this process n times, where n is 2 pi, as pi divided by 2 theta square, then what you will end up having is basically this decay, inverse decay, and this neutrino having covered all angular positions from minus pi to pi. This is just a random walk argument, okay? So the number of steps that's taken is n, as said. If you evaluate this, this is roughly equal to theta minus 2. Okay, so it takes n steps, random steps, for new H to visit all angular positions from minus pi to pi. And so because you're covering all the angular positions, we call it a coverage time. And the coverage time you can write down as basically the number of steps that you need multiplied by the time scale of the decay. Okay, so that's the time scale of the decay, and then you multiply by the number of steps. And that's your coverage time scale. And that's essentially what these guys did. That was their argument. And they used, in particular, this second paper, used that coverage time scale, and they interpret that coverage time scale to be the isotropization time scale. Okay, and assuming massless decay products, they derived a lifetime on the for the neutrino, lifetime bound for the neutrino that goes something like this. Okay, so 10 to the 9, and then you have this m cube dependence. There are many updates to the number since with better data and somewhat improved modeling. But the thing is that no one really questioned the modeling, the previous argument for the next 15 years until we came along and decided to think about whether it made sense or not. And as it turns out, what I told you just now about the coverage timescale is only the first half of the story. There's more to it. Okay, and the punchline is that it is not the isotropy timescale, and here's the reason. So here we have the same schematic again. You have the new H that is decaying. And since it's a decay process, whether the X particle goes this way or this way, the probability is equal. Okay, it's just totally random. But then you move on to this stage where the X particle recombines from something from the background. And here's the tricky part. And that is because if your background is not isotropic, then the emission probability of this final new H will be different depending on whether you are combining with, an X particle from the background in this direction or that direction. And in fact, if you have a strong anisotropy, such as like this one shown here, this direction is the direction that is favored. So your random walk is biased, in other words, because your background is not isotropic. Okay? It's biased towards the anisotropy of the background, in fact. Now, the bias that we would expect, the anisotropy in the background that we would expect is small. It's cosmological, it's 10 to the minus 5. So the neutrino will still take about n, which is equal to theta minus 2 steps to visit all the positions from minus pi to pi. But the thing is that if you look at what happens after one coverage time, what you'll find is that there will be a higher concentration of steps in the direction of the anisotropy. Okay? Now, that's just for one particle. Okay? And now if I consider what happens to a whole ensemble of random walkers. Okay, so that's a whole, billions and millions and Avogadro numbers of neutrinos random walking all at the same time, like so. Then what would happen to this ensemble is that after one coverage time, this neutrino ensemble would end up being kicked into a distribution that roughly reflects the anisotropy of the background. Okay, so in other words, after one coverage time, you have not managed to isotropize the system whatsoever. Okay, you have actually made it as anisotropic, almost as anisotropic as the background. Now I say almost, I didn't say exactly, and that is because when you look at the recombination of X with another X from the background, the heavy neutrino that gets emitted is always at an angle relative to the anisotropy. Okay, so that's just the decay. It's nothing we can do about it. So in other words, there will always be a tiny little bit of loss of anisotropy after one step. It's just a tiny bit of loss, not a lot. Okay, so here's a picture here illustrating what's happening. If I look at the initial anisotropy, so here's quadruple anisotropy, the yellow line is the initial state. Then after one coverage time, what would happen is that you'll bring it down to the red line, okay? And the amount of loss of the anisotropy is of order theta square, okay? That's easy to calculate. You just take the initial anisotropy, smear it over an opening angle of theta. This is the result that you would get. So what it means is that if you want to use this process of decay and inverse decay to wipe your anisotropy, in other words, you want to bring the yellow line down to the blue line, what you need to do is to keep repeating coverage another m times, where m is equal to theta to the minus 2. Okay? And so that gives us the true isotropization timescale, which is actually this angle multiplied by the coverage time, and we calculated coverage time in the previous slide, so that's the final expression. Okay, so relative to the old expression, there's an other factor of the angles. Okay, that was hand waving, but as I said before, these things are calculable. And in fact, chronologically, we calculated it first before we even realized what was happening. It took us a year to realize what was happening, to come up with an explanation. And in fact, with a bit of algebra and all that, you can even write down a rather neat damping equation for the anisotropic stress, like so. So this is F L larger than 2, so that's a second L equals 2 or larger than 2 multiple moment. This is in the form of an exponential damping, so I have a minus sign over here, and all of this horrible looking thing here is basically the inverse of the isotropization timescale. There's a prefactor, which is order 1. This here is the booster decay rate, and all of these terms over here are essentially just the emission angles that we talked about before. Okay, these two emission angles square. And the thing, when you think about calculating things properly, is that often you end up with these nice bonus features, like this factor over here. And this actually describes relativistic to non-relativistic transition. it's the factor is about 1 to 10 when the neutrinos are relativistic, and it quickly drops to 0 when the neutrinos become non-relativistic, which makes sense because this whole game of relativistic free streaming damping only works when the neutrinos are ultra-relativistic. So you should have this damping thing, which, as said, pops out naturally if you do the calculation. It's model independent in the sense that any kind of Lorentz structure of your interaction will be, in any case, encoded in the decay rate, and the rest of this stuff is just kinematics. So here's some revised lifetime bound. So we consider various scenarios. So if, for example, A1 here corresponds to the normal hierarchy, so it's over here. We've kept nu1 as a free streaming particle, and then we have nu3 decaying to nu2. So that's the first scenario, so on and so forth. Okay. Looks kind of ugly. They look very different, but phenomenologically, they're really only just two independent parameters, y and x. So y is like an effective isotropization rate, and x is essentially just the mass of the decaying neutrino. So here are the signatures, not terribly interesting. So what we've done is to basically fix x at different values, so different decaying masses, and then we found constraints on y using the Planck 2018 CMB data. And then after we found the constraints on y as a function of x, we translated these constraints to a revised lower bound on a neutrino lifetime that looks something like this. Okay. So the key things to note is that here there's a prefactor 1.2 times 10 to the 6. If you compare with the old constraint, which misidentified the coverage timescale with the isotropization timescale, this prefactor is 10 to 9, sorry. And another thing is that you have this m to the power 5 over here, and they had m to the power 3. Okay, so these are two key differences. And also new here in our new bound is the fact that we have allowed for the possibility that there's a mass gap, finite mass, that the lighter neutrino is not massless. So there's a phase space factor that comes into play over here. And then of course, we also have this relativistic to non-relativistic factor. If this doesn't look very good to you, we've also translated this into numbers. So for something like, well, like nu3 going to nu1, 2 in the normal hierarchy, the bound is like of order 10 to the 5 seconds. If you want to be adventurous and look at only decay from nu2 to nu1, so with a very, very tiny mass gap, then the lifetime bound is actually only in a few hundred seconds. Okay. Some plots just to show you how this bound fares relative to other constraints that are out there. My supernova constraint is old, so I should update this. This is not right, but you can also see that Ice Cube also has a constraint which is kind of down here. But the main thing is that they are saying that they're forecasting that they'll be probing this region. Again, I was reading the paper at face value. I don't know if if the modeling is actually completely compatible with what we were doing. But at least it looks like our bound here is sort of sitting in the Ice Cube region. Okay, so that's another one. That's for the normal hierarchy, similar. Oh yeah, in case you were wondering, here's a dashed line, and it's a solid line. Solid line is our new result. The dashed line is what would happen if you did not take into account the phase space factor coming from the mass gap. Okay. Anyway, I think that's all I want to say, and I'll leave you here with my summary, and thanks for your attention.
All right, thank you for the really nice talk. Do people have questions or comments?
Thank you. Just for detail to understand the calculation when you do the full Boltzmann equation. So when you do that, nu H was one of the 3 mass eigenstates, and the phi boson, there was none initially, or is there some?
Yeah, so in our particular scenario here, there's no existing population of phi. So essentially what happens is that the decay kicks in after neutrino decoupling. So the phi particle population is essentially just sucking energy out of the neutrinos.
So I guess they share the same anisotropy as the initial neutrinos?
Yeah.
Okay, ask one quick question since, oh, there was another.
I keep asking, yeah.
Go ahead.
The ice cube limit, can you say a little bit more about what the signature is and how they extract that?
I
Or-
think the ISQ people here know better than I do.
Okay.
I just read their paper and just
Okay.
put their limits. I cannot really say exactly what they're doing.
Okay.
Yeah.
So that those ice cube constraints come from the flavor ratios of physical neutrinos. Essentially, the fraction of electron neutrinos changes if you only have the first or the third mass states are surviving. So it assumes they have all fully decayed. And that's currently mostly statistically limited in our capacity to measure the flavor ratio. And probably not going to improve that much until we have Gen 2.
Any more questions or comments? Paolo.
Okay, just to be sure, but the anisotropy of the universe is considered decaying with time.
Anisotropy of the universe.
Anisotropy, yes, because should decay with the expansion of the universe, no?
In what sense? I mean, like,
You start with the universe with a certain amount of Bianchi model, no? Okay, so if you start with a certain amount of anisotropies, this anisotropy, if you are in certain cause decay with, I think, with expansion, with time, with a certain power law.
yeah, I guess so. Yeah, maybe. But I mean, I can't. I haven't looked at that equation. I wouldn't really say that. Yes, it does. Oh, okay, but
okay. No, because the question is that is okay with certain, let's say, type of Bianchi model. There are 9 Bianchi models. In some Bianchi model, the anisotropy of the universe increases with time.
Yeah.
Because coupling between the density, which is an anisotropy part,
Yeah.
and expansion.
Right.
In this case, I would like to know what happens to this computation.
So these people who look at these Bianchi models, they are normally looking at pretty late time effects, right? This is an early time effect. This is around CMB times.
Okay.
So the question is, I mean, this is coming entirely from the CMB and it's physics at the CMB epoch. So if these anisotropic models are not operative at that time, that doesn't really.
No, they are used. Eventually, they were used because there was the Russian school in 1970.
Yeah.
They wanted to isotropize the universe with neutrinos at the very high level of neutrinos. This
I see.
was
Okay.
my thesis. I did this with other people, so I remember this. And of course, the point was that certain, as far as neutrino couldn't do certain Bianchi model because they were a late time, let's say, a sort of anisotropy was raised at late time. Especially if you were in a model with lambda difference.
At late times.
Late times, yes.
How are the neutrinos doing? And I mean, they don't really, there's hardly any of them in terms of energy density at late times. So how are they getting rid of the anisotropy due to some initial anisotropy? I mean, just wondering.
Yeah, this means that in these models, you have say, an anisotropy in the universe, in the space dimensions of the universe, not only in the expansion of the universe.
Yeah.
So this one, but of course, this maybe has nothing to do with your case, because if your case is very, very, say, early time, at early time, all models are Bianchi #1. So it's like that you have anisotropy only in the expansion of the universe. And the case is for a certain period. And then if you are in the bad, the universe starts increases a lot. It is the reason why then you got at the end the inflation.
Mhm.
because before the inflation, people thought that the isotopization of the universe was done by neutrinos in this way, because this was the way which the big Russian, they went
Okay,
to.
yeah.
So just to.
Okay, I mean, I don't know, it's
So
also the way of the history.
Okay, we should probably run off to the coffee break and Sergio can ask the question later.
So so the BBM bound is very short time, right?
Yeah, yeah.
Why I would expect that bound to be, I don't know, 100 seconds, something like that, or
BBM?
1,000, yeah.
No, the BBM bound is actually, it's basically they were looking at, okay, so the paper I got that out of was Miguel Escudero. I actually just stealing his bounds actually. So what they were looking at is they were looking at 2-to-2 scattering. So you could have, the same kind of model that would give rise to that decay process would also give rise to scattering. And so if you have that kind of scattering happening before neutrino decoupling, you'll end up generating an N-effective. So the BBN bound is really a constraint on the N-effective as a result of you generating some phi particles before neutrino decoupling.
Yeah, but it would also distort the momentum distribution, right? And I mean, if the case at that time, I would expect the distortion of the momentum distribution to affect. I mean,
Yeah.
you have something like 10 to the minus 2 second. I mean, that is immediately after the coupling would immediately
Yeah.
affect.
That's what they wanted to do. They would basically just ask. I mean, they were just asking what happens now if you say so. You want you want the bound to be at 100 seconds.
Or 1,000 or whatever. I mean, much later, because this is like right after decoupling, it would be, I would expect this to affect any time, like 10 to the minus 2, 10 to the minus 1.
You probably can do that, I would imagine. Yeah, that you might change your weak rates if that's what you want to do, right? You change your weak rates because you're upsetting the spectrum. It's possible.
Yeah.
I haven't seen it done, but this is really just an ineffective bound.